Hello and welcome. Today, we're going to dive into the incredible journey of one of the most powerful and yet humble substances on Earth, steam. We're going to find out how ordinary water transforms into a true industrial workhorse. You know, the stuff that literally powers our world. And right here, this is the secret sauce. The real magic of steam is its unbelievable ability to absorb, store, and then move huge amounts of thermal energy. I mean, this single property is why it became the lifeblood of the Industrial Revolution and why it's still so critical today.
So, okay, we know it's powerful, but how does simple water actually pull off this radical transformation? That's the big question we're going to answer. We're going to follow its journey from a plain old liquid to a super high-energy gas.
To really wrap our heads around this, we're going to follow the story of just a single kilogram of water. Think of it as our main character. We'll track it as it soaks up heat and changes its form, step by step. This is the theory, the foundation for everything else we'll talk about.
And here's our roadmap. Our little kilogram of water is going to pass through these 5 distinct states. We'll start with cold liquid and end up with this high-energy, totally invisible gas. So let's get this journey started.
All right, states 1 and 2. Now, this feels pretty normal, right? We add heat, the water gets hotter, we can literally watch the thermometer climb. All the energy we're putting in at this point is doing one simple thing, raising the temperature up to that boiling point.
And that energy we just added, it has a name, sensible heat. It's called that because you can sense the change. You can feel it getting hotter, you can see it on the thermometer. But here's the key. It's still 100% liquid water. The state hasn't changed. Yet.
Now, this is where things get weird and really interesting. As soon as we hit 100 degrees Celsius, the thermometer just stops. It freezes in place. We're still pumping heat in, but the temperature isn't budging. So what's going on? Well, now all that energy is being used for a much tougher job, physically breaking the bonds between water molecules to turn the liquid into gas. This bubbly, turbulent mix is called wet steam.
This hidden energy is called latent heat. And folks, this is the real powerhouse of steam. It's this massive amount of heat that gets soaked up without changing the temperature one bit. And it's all that stored up energy that we can harness to do incredible work later on. This isn't just the energy of getting hotter. This is the energy of transformation.
So once that very last droplet of water has finally turned into vapor, boom, we've hit state 4, dry saturated steam. It's now a pure invisible gas. And if we keep adding heat, well, guess what happens? The thermometer starts to climb again. This is our final form, state 5, superheated steam, which is just a totally dry gas that's been heated way beyond its boiling point.
Okay, so that was the physical journey, the what. Now let's pivot and get practical. Let's look at the engineer's toolkit. How do people actually measure, quantify, and work with these different types of steam? This is where we get into the numbers.
So let's do a quick recap of our 3 main players. You've got wet steam, which is that messy mix of vapor and water droplets. Then you have dry saturated steam. That's 100% vapor, but it's sitting right at the boiling point. And finally, superheated steam, 100% vapor, but at a temperature above the boiling point. Keeping these 3 straight is absolutely key.
So why do engineers go to all the trouble to get to that final state? Because superheated steam is an absolute superstar. For one, it packs way more energy, which makes engines and turbines much more efficient. But maybe even more important, it's completely dry. And that is vital, because at the incredible speeds inside a turbine, those little water droplets in wet steam act like tiny bullets, just eroding and destroying incredibly expensive turbine blades.
To deal with that wet steam phase, we have to know its quality. And that's where the dryness fraction, which we call X, comes in. It's just a simple ratio, a number between 0 and 1. If X is 0, you've got all water. If X is 0.9, your mix is 90% steam and 10% water. And if X hits 1, you've got perfectly dry steam. Simple as that.
So how do we actually calculate the total energy in our steam? Well, for that, we use a value called enthalpy, shown by the letter H. The easiest way to think about enthalpy is as the total energy budget of our kilogram of water. It's the sum of all the heat we've added, from the very beginning, to get it to its current state. For any thermal engineer, this is the number that matters most.
And look at this. This formula just brings everything we've learned together so beautifully. To find the total energy, the enthalpy of wet steam, you just take the sensible heat, HF, which got us to the boiling point, and then you add the portion of the latent heat, HFG, that's been absorbed so far. And how do we know that portion? We use our dryness fraction, X. See, it all just clicks into place.
And the best part is, this logic just keeps building. For dry steam, our dryness fraction x is just 1, so we've absorbed all of the latent heat. Simple. And for superheated steam, well, we just add one more little term on the end to account for that extra sensible heat we added to raise the temperature past the boiling point. It's really elegant.
Now, engineers aren't just guessing these values in the field. They use official steam tables, kind of like this simplified one here. And I want you to look at this, because there's a fascinating trend. As you crank up the pressure, the boiling point goes way up. That makes sense. But look at the latent heat. The amount of energy it takes to make that leap from liquid to vapor actually goes down.
And this trend leads us to a truly wild destination, the critical point. At an insane pressure of over 221 bar, the latent heat you need to boil water drops all the way to 0. At this exact point, water doesn't boil. It just instantly flashes into steam. The line between liquid and gas completely disappears. It's a truly bizarre and powerful state of matter.
So you see, from the sensible heat that warms the water for your tea, all the way to the superheated steam spinning a massive power plant turbine, understanding this journey is really about understanding energy itself. The principles are exactly the same, it's only the scale that changes. It really makes you wonder, doesn't it? What new ways will we find to harness this incredible transformation in the future?